Alright, welcome to section 6.2, Antiderivatives and the Indefinite Integral. So in our last section, I made a comment that antiderivatives and integrals were closely related, and today we're going to be getting into that a little bit more. So we have seen so far something called the definite integral, okay? And the definite integral has the bounds of integration. All right, so that was from A up to B. Okay, our indefinite integrals, no bounds. All right, and we are going to get into explaining how that works here in a minute after we do a little bit of warm-up. Basically, we're going to remind ourselves how we take derivatives because it's been a little while. All right, so let's first look at f of x is equal to 5e to the 2x. And so we want to take the derivative. All right, in this case, we want to use an exponential rule. We can also pull out the constant. So it's just the derivative of this e to the 2x. And we have an exponential rule that says we need to pull the 2 down, but then e to the 2x, everything else stays the same. If we multiply this out, we end up with 10 e to the 2x as our final derivative. All right, let's look at another one. Let's look at g of x is equal to the natural log of 7x plus 1. So if we remember, we have the natural log function, okay, which means it's going to be 1 over everything that's on the inside. So g prime of x, it's going to be 1 over 7x plus 1. But we need to use our chain rule. If we remember that, that says we need the derivative of the inside function. So we took our derivative of the outside function, that was here, and now we need to multiply it by the derivative of the inside function. I apologize if you can hear my dog in the background. I took her squeaker ball away from her and she's upset about it. So the derivative of the inside function here is just going to end up being 7. So we have 7 over 7x plus 1, and that is our final derivative for g of x. And lastly, we'll look at h of x, which is the quotient 2 over 2x minus 1, which means we need to use the quotient rule. So h prime of x, the quotient rule is the derivative of the top times the bottom. So the derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared, right? Okay, so the derivative of 2, or any constant, is 0. So 0 times anything will end up being 0 minus this derivative of 2x minus 1, which is just 2, still times 2, over 2x minus 1 squared. And so we get negative 4 over 2x minus 1 squared as our final derivative. All right, that's just a good refresher on how to do a little bit more complicated derivatives. All right, so now we're going to get into what an antiderivative is. All right, and we're going to start trying to think of the backwards, like undoing a derivative almost. Okay, so an antiderivative can be thought of as undoing a derivative, or essentially going backwards. So, for example, if we have lowercase f of x is equal to 2x, I want to come up with an antiderivative, capital F of x. I want to think of a function whose derivative is 2x. So if we think about the power rule, we know that if we have x squared, our power rule would be bring this down, subtract 1, so we'd end up with 2x to the first power. All right, so this is an antiderivative for 2x, would be x squared. How about x squared plus 1? Does that work as an antiderivative? Or x squared plus 17? Take the derivative of both of those. We get 2x because the derivative of a constant is 0, right? Since the derivative of a constant is always 0, we need to write that we have x squared plus c. Okay, so we need to write x squared plus c, where c is the constant of integration. So that's what we call c. And x squared plus c is a family of antiderivatives of 2x. Okay? Emphasis on family there. So essentially, we have an unlimited number of options of antiderivatives. All right? X squared plus any constant is an antiderivative of 2x. All right, I need a little bit more room because we need to talk about notation next. So for notation, we're going to write the indefinite integral. So that means no bounds. I'm not going to write a and b. So the indefinite integral of f of x with respect to x is going to be capital F of x plus c. So we're going to make a note that the indefinite integral, all right, this gives a family of functions and a definite integral, which is what we've been dealing with for this entire course. Okay, so the indefinite integral, that's just going to give us a value, right? It gives a number. So the definite integrals are what we have been plugging into our calculator to get an exact number, an area. All right, so let's jump into our first example. We need to determine which are antiderivatives for each given function. All right, so first we're going to look at A. We have f of x is equal to 30 times x to the fourth. So we need to think about a possible function that when we take its derivative, we get 30 times x to the fourth. All right, so let's look at our first example, this capital F. If we take the derivative, we'll end up with 120 times 3 x to the second, right? Well, that's not what we are looking for. Okay, how about g of x? Let's look at g prime of x. Well, we'd get 6 times 5. Okay, that's 30 x to the fourth. Hey, that would work. That gives us 30x to the fourth. Okay? And just for completeness, if we go ahead and look at h prime, we would get 30 times 5 x to the fourth. So close, but not correct, right? So we're going to go ahead and choose this g of x function. So g of x is an antiderivative for f of x for part A. Okay, let's look at part B. So we have 2 times e to the x. Again, we're looking for a function whose derivative is 2e to the x. Let's look at the first one here. So f prime of x, so the derivative of e to the x, that's one of the special ones, right? It's just e to the x. How about the derivative of g of x? All right. Well, in this case, we have an exponential rule that says we pull the 2 down, but then we leave everything else the same. So we have 2x up here. Again, pretty close, but not exactly correct. Let's look at h of x. Let's take the derivative of h of x. All right. So we have 2 times the derivative of e to the x, which is e to the x, plus the derivative of 1, which is 0. So we're done taking the derivative, and we find that h of x is the antiderivative for part B. And now let's look at part C. So we have h of x is 4 divided by x. Okay, so let's go ahead and take some more derivatives and see which one is going to line up. Okay, so f prime of x, here we have the function is 4 times the natural log of x. We know that constants can come in and out of derivatives, so we have 4 times the derivative of the natural log of x, and we know the derivative of the natural log is 1 over x. Okay, so that looks pretty good. That looks like what we want. Let's go ahead and double check the others, 1 for practice and 2 to make sure there's nothing else that gives us the same answer, because that is possible, right? We learned that antiderivatives are not necessarily unique. So let's look at g prime of x. We have the natural log of 4x. So this is going to be a chain rule, right? So we need 1 over 4x, so that's the derivative of the outside function, times the derivative of the inside function. So the derivative of 4x is just 4. And then the derivative of 2 is just a constant, so that gives us 0. So our 4's end up canceling out, and we just get 1 over x. Okay. And finally, we have h prime of x. Well, first of all, I'm going to go ahead and rewrite this as 2 times x to the negative 2. I just don't want to have to use the quotient rule here, so I'm just going to move it up and then use a power rule. Okay, so we have 2 times, let's see here, negative 2, x, subtract 1, negative 3. So we get 2 over 2x to the third, and yeah, that's not what we're looking for either. So f of x is our antiderivative for h of x for part C. Okay, so now let's look at a few antiderivative rules. Okay, so first of all, we have a power rule. Okay, this is similar to our derivatives, but in this case, we are adding 1 to the exponent and then dividing by that new exponent, n plus 1. We also can't forget our constant of integration. Okay, always remember that plus c, it's very important. So, and this only works for when n is not equal to negative 1. That's the special case with the natural log, remember? All right, so then we have, what about the antiderivative of a constant, where k is some constant? Well, you're just going to get the constant times x plus c. Again, similar to derivatives, we can split integrals over sums and differences. So if we have the integral of f of x plus or minus g of x dx, we're going to end up with the integral of f of x dx plus or minus the integral of g of x dx. Again, making sure you're always capping off that integral with a dx or whatever variable that you are using in your problem. Okay, then we have a constant multiple rule. So when we have a constant times a function, we can just pull that constant right out of our integral. Okay, we're almost done here. We have our natural log. So this is the instance where that power was to the -1. So the integral of 1 over x is going to be the natural log, but make note that it has to be the absolute value of x, and then plus our constant of integration. Okay, and finally, we have the exponential rules where we have e to the kx dx, and we get 1 over k e to the kx. Again, plus our constant of integration. All right, so now that we got through all of our rules, we're going to look at an example on how to use them. So for example 2, we want to find the general antiderivative. Okay, so we're just finding the general, which means finding the whole family, so using that plus c. All right, so we want the antiderivative of 2x dx. We're going to use our constant multiple rule, which says we can pull the 2 out. So now we just have the integral of x with respect to x. Okay, so this is our power rule where n is equal to 1. So we'll leave this 2 out here. N is equal to 1, so we need x to the n plus 1 divided by n plus 1. And then we need to add that constant of integration. So we have 2 times x squared divided by 2. Our 2's cancel out. We get x squared plus c, and that is our final answer. Okay, let's do it again. Let's look at part B. We have 3x squared minus 3. So we want the integral of 3x squared minus 3 with respect to x. Remember, we can split integrals over sums and differences. So we have 3x squared dx minus the integral of 3 dx. Then we can use our constant multiple rule to pull this 3 out front, and now we have x squared dx minus 3 dx. Okay, so then we have 3 times, well, we have x squared. So this is our power rule with n is equal to 2. So we're going to have x cubed. So that was n plus 1. So 2 plus 1 is x cubed divided by n plus 1. So divided by 3. Okay. Oh my goodness. Okay. Minus, this is our integral of a constant rule when we just said it was going to be the constant times x. All right. Plus c. Now, I'm going to stop here for just a second and say you might be thinking, should we not have 2 different c's? Or should we have plus 2c or something like that? And it's a little bit difficult to explain other than c is any number. We don't know what number it is until we get to finding the unique values later on. Okay? And so if you multiply c by 2, or if you do anything with any other number to c, it's just going to kind of get absorbed into this all-encompassing constant, okay? So that's why we don't need to write plus 2c or something. It's just c no matter what, okay? And so then these 3's cancel out and we get x cubed minus 3x plus only our 1c, and that is our antiderivative for part B. Okay, let's keep going. Let's look at part C. Here we have f of t, so we need the integral of 12e to the 6t plus 1. Well, let's go ahead and split this up. We have the integral of 12e to the 6t plus the integral of 1, the integral of 1. We can pull that constant out, so we just have the integral of e to the 6t plus the integral of 1 dt. So here we have 12. So the integral of e to the 6t, this is one of our exponential rules, right? Where we're going to have e to some constant times our variable. So we're going to put 1 over that constant. So 1 over 6 e, and then we leave everything else alone to the 6t, okay? Plus, now the integral of a constant is that constant times the variable. So 1 times t, which is just t. And then we need our constant of integration. Okay, let's simplify. We have 12 divided by 6, so we have 2e to the 6t plus t plus c, and that is our final answer for part C. All right, let's do one more. We have the square root of t. I'm going to go ahead and rewrite this as t to the 1/2. All right, so we have the integral of t to the 1/2 dt. So this is a power rule, but with a fractional exponent. Okay, so we're going to have t to the 1/2 plus 1 divided by 1/2 plus 1 plus c. All right, let's clean this up a little bit. 1/2 plus 1. Well, 1 is 2 halves, so 1/2 plus 1 is 3 halves. All right, so that means we have 3 halves on the bottom plus c. And when we have a fraction in a fraction like this, we can actually flip and multiply. So this is 2/3 times t to the 3 halves plus c. Okay? And this is our final answer. So nothing crazy happened between the last two steps. It's just some properties of exponents. All right, but if you need any more clarification, please shoot me an email. All right, so let's look at example 3. We need to determine if the following will result in a number or a family of functions. So those are our two options, a number or a family of functions. And we learned that the definite integral will give us a number, and the indefinite integral will give us a family of functions. So that being said, let's look at part A. We have the variable x plus an indefinite integral. So this is going to give us a family of functions. Part B, we have a definite integral. Okay, so a definite integral is always going to give us a number. And let's look at part C. So we have an indefinite integral, which gives us a family. We have a definite integral, which gives us a number. But overall, we just have a family plus a number, so it's still a family. Okay? Let's look at part D. So we have the indefinite integral of f of 10. So f of 10 is where we have the function f. We plug in 10 for our x value. That's going to give us a number. So now we have the indefinite integral of a number, which is going to be a family. So we've learned a lot about the families of antiderivatives. Now we're going to make a note that given additional information, we are able to find unique antiderivatives. Meaning, find one value for the constant c. Okay? So example 4 is going to walk us through this. So we want to find the unique antiderivative given the set point. So that's our additional information that we needed, is our f of 1 is equal to 10. So let's see how this is going to work. First, we need to take the antiderivative, right? We need to take the integral. So let's go ahead and do that. We're going to take the integral of 2x plus 3x squared minus 7 with respect to x. We're going to break this up into 3 different integrals. So we have the integral of 2x dx plus the integral of 3x squared dx minus the integral of 7 dx. Using our constant multiple rules, we'll have 2 times the integral of x dx plus 3 times the integral of x squared dx minus the integral of 7 dx. So then we have the power rules. So we have 2 times the integral of x. So that's going to be x squared divided by 2 plus 3 times the integral of x squared. So that'll be x cubed divided by 3 minus the integral of 7, where 7 is a constant. So it's going to be the constant times the variable. So we have minus 7x. And we can't forget our constant of integration. I will make a note here that it's very easy to get confused between derivatives and integrals or antiderivatives. So just always take your time, take a deep breath through these new problems. The number of times it's possible to say, oh, it's a constant, so it's 0. That's in derivative world, right? So in antiderivative world, it's then the constant times the variable. Okay. So let's clean this up a bit. The 2's are going to cancel out, and we'll have x squared plus the 3's will cancel out. So we have x cubed, and then minus 7x plus c. So we've found the general antiderivative. Okay. But we're asked to find the unique antiderivative, so we need to find what that c value needs to be. Okay, and the way that we do that is we use this additional information that we were given. F of 1 is equal to 10. So how do we do that? Well, this antiderivative is our capital F. So what we just found was our capital F of x. So we know we were given that capital F of 1, well, we can plug 1 in everywhere to get 1 squared plus 1 cubed minus 7 times 1 plus c, and we're given that this must equal 10. So we set this equal here, and now we can solve for c. So we get 1 plus 1 minus 7 plus c is equal to 10. So we get negative 5 plus c equals 10. So c is equal to 15. All right, so we wanted to find the unique antiderivative. All right, so f of x, capital F of x, is x squared plus x cubed minus 7x plus 15. And that is our unique antiderivative. Let's look at part B. So again, we want to find the unique antiderivative of the function, and we are given a point. So we want the integral of 3 over x dx. Well, our constant multiple rule says that this is 3 times the integral of 1 over x dx. And we have another rule that says, well, this is the natural log. So we have the 3 times the natural log of the absolute value of x, and then we need our plus constant of integration. All right, so then we have f of 1 is equal to 9. So f of 1 is going to be 3 times the natural log of 1 plus c needs to be 9. So we can use our calculator, or we can know that the natural log of 1 is equal to 0. So we have 0 plus c equals 9, which gives us c is equal to 9. So our unique antiderivative is 3 times the natural log of the absolute value of x plus 9. Okay, and our last example is example 5. So here it says you decide to go on a road trip to Nevada starting from your home. On your trip, you find that your car's velocity can be measured by this function here. And it asks us to find the function for your position from your home during your trip to Nevada. And we must include the correct value of c. That's supposed to be correct. Correct value of c. There we go. All right, so let's remember how position and velocity are related. Velocity is a rate of change. Specifically, it's the rate of change of position. So we need to go backwards. It was the derivative of our position function. We need to go backwards from our velocity to our position, which means we need to take the integral, or the antiderivative, of our velocity. So our position function is normally given as s of t, and that's going to be found by taking the integral of v of t. So it's our 2t squared minus 3t plus 8 dt. So this is going to give us 2/3 t cubed minus 3/2 t squared plus 8t. And we can't forget our constant of integration. So I skipped a few steps there, but it was just power rules all the way through. Okay. So we found our general integral, but we need to find our specific integral because we need to find our plus c. So we need an additional piece of information that we were not given. Or were we? Okay, so let's look here. We decide to go on a road trip to Nevada, and we're starting from our home. There it is. There's our clue. We're starting from the house, and the position function is position from home. Okay, so this tells us that at the very start of our trip, so at t is equal to 0, we were starting at the house. So we hadn't left the house yet, which means our distance from the house had to be 0. S of t had to be 0. So S of 0 equals 0. This is our extra information that we needed. So we need S of 0 is going to be 2/3 0 cubed minus 3/2 0 squared plus 8 times 0 plus c, and all of that needs to be equal to 0. All right. And it just gives us that c is equal to 0. So our unique antiderivative for S of t is simply 2/3 t cubed minus 3/2 t squared plus 8t, and c was equal to 0, so we don't need to write plus c. And that's our final answer. All right, so that wraps up section 6.2. I know first starting out calculating integrals can be a little bit tricky, so feel free to send me any emails with any questions. I'm always happy to help. Don't forget to take the comprehension quiz, and I'll see you in the next lecture.